Good afternoon, everyone. I'm Gaia Javier from UNSW Sydney, and today we will be presenting our work on advanced production line monitoring with time lag sequential analysis. Let's start with a short icebreaker based on the Spot the Imposter game. But instead of spotting the imposter, let's spot the anomaly. Can you identify the anomaly in this picture? Well, kudos to you if you found this real dog over here. Now, anomalies exist everywhere, even in solar cell production lines. Our expectation is that the mean performance of solar cells fabricated in a production line is constant. However, in reality, variations are inevitable, and this can be due to changes in the quality of input material, processing conditions, and environmental parameters. There are two types of variations that could occur in a production line. The first one is called special cause variations, which are caused by specific factors such as equipment breakdowns or operator errors. The second one is called common cause variations, and these are inherent in the production process and occur randomly. Common cause variations are generally preferred as they can be predicted, making random variations more desirable from a variability perspective. So let's remember, random variations are more desirable. Several methods have been developed to monitor variations in a production line. However, these methods have their own limitations, as you can see in this table over here. Most importantly, the existing methods lack the capability to quantify random variations. Therefore, the main objective of our study is to address these limitations by proposing an alternative approach. Specifically, we want to develop a simple and reliable metric for evaluating critical aspects of the production line, and second, to evaluate the feasibility of this metric through simulations and actual measurements from an industrial line. Our proposed methodology is based on lag-sequential analysis. So for example, we have data of cell 0 to cell n represented by x0 to xn. What lag-sequential analysis does is that it shifts the original data by certain timestamps. So for lag 1, you shift the original by 1 timestamp, lag 2, 2 timestamps, and so on. You can now compare the lag with its original. If you want to compare the lag 1 with its original data, you can subtract the 2 and you'll have a lag 1 difference data. The lag difference data is essentially a measure of the cell-to-cell variance. We then developed a factor called the ret factor, or RF, which is equal to the variance of the lag difference data divided by twice the variance of the original data. By the way, this is ret. So what does the ret factor, or RF, mean? If RF is equal to 1, then variation is random, and if it's not, variation is not random. We simulated several cases to test the feasibility of the RF. However, due to time constraints, I will only present 2 cases. So for the first case, we simulated 10,000 cells with a random data. This is the efficiency as a function of time, and this is the corresponding RF versus lag. And because the data is completely random, as expected, RF reaches unity already from lag 1 and stays constant all throughout. Now what if we have a non-random data? And for this case, we vary the mean for every 300 cells, and this is the efficiency as a function of time. And this is the corresponding RF versus lag. You can then infer 3 critical aspects of a production line based on this figure. The first aspect is the statistical touch point. This is the lag where RF reaches unity. And because we varied the mean for every 300 cells, it's expected that 300 is the statistical batch point for this set of measurements. So this is basically the batch size where cells are statistically independent of each other. The second one is the yellow region, which is the region before the statistical batch point, and it indicates the level of randomness of a given lag. For example, for lag 100, RF is equal to 0.8, meaning 80% of the variance is random for this lag, and 20%, which is the remainder, is related to mean shifts. The third one is the red region, which is the region after the statistical batch point. So it's a measure of the changes in the production line's variance about the mean. If you see high fluctuations in this region, it indicates high instability in a production line. And that's what we see in this figure over here. So what makes a good production line? A good production line should have a low statistical batch point, high RF at the yellow region, and stable RF at the red region. We implemented the RF method on experimental data. Note that solar cells at the end of the line are characterized for quality control and binning. And one of the characterization methods used is current voltage or IV testing to measure electrical parameters. And another one is electro or photoluminescence ELPL imaging to capture spatial information and assess defects. We implemented the RF method on 17,000 IV measurements of multicrystalline silicon cells. This is the normalized efficiency as a function of time. Now you might agree with me that by just visually inspecting it, it's hard to determine whether these variations are random and whether this is a good production line or not. So we compute the RF versus lag, and this is the result. And you'll see here that the statistical batch point is 500. So we then wondered, why is this so? We assumed that this is due to the diffusion process in the production line, and this was further confirmed by our industry partner. And for the yellow region, we see that already at lag 1, 80% of the variance is already random, and you'll see small fluctuations in the red region. So let's remember, these are the criteria for a good production line, and since all of these are met, we can say that this is a good production line. You can now extend the applications of the RF methods for root cause evaluation, real-time monitoring, and image analysis. So let's go first. RF for root cause evaluation. Note that the efficiency can be due to several parameters such as the open circuit voltage, short circuit current, series resistance, etc. From simulations, the RF versus lag graph of the efficiency effectively captures the most dominant source of variance. So we then apply the RF method to other electrical parameters, and these are the results. And from a simple correlation analysis, we learned that the VOC contributes most to the variance of the efficiency. So far, we have used the RF method on static data. Now what if we have dynamic data? We can now define a window and then move that window as soon as you get new data. And for every window frame, you compute the RF versus lag and then compute or compare these graphs with each other. As an example, we use the real-time monitoring method on the normalized efficiency as a function of time. This orange window right here defines thousands of cells, and this is the corresponding RF versus lag for this window. And these are values for the three aspects that we've been monitoring. And this is for window 2 and 3. Note that the three critical aspects didn't change. Therefore, there is no apparent change in variability for this production line. Now we proceed to RF for image analysis. Here you have 3 EL images of solar cells, and by the looks of it, you can tell that these are defective cells. Now we've been doing several methods to determine whether cells are defective or not, but we don't really know whether these defects are random or not. We can actually translate these spatial information to one-dimensional information by taking image metrics such as the mean, standard deviation, etc. And once you have the image features that you like, you can plot it as a function of time and compute the RF versus lag. So to determine whether these defects or the defects in this production line are random or not, we take the bad area percentage. So with that, this is the RF as a function of lag. And since at the very low lag, the RF is already equal to 1 and stays constant all throughout, we can say that the defects or the presence or the introduction of defects in this production line is random. So the next time you have time series measurements and want to know whether the production line is good or not, you might want to consider our RF metric, which can be used to infer probable batching, degree of randomness, and stability in a production line. And extended applications of the RF method include root cause evaluation, real-time monitoring, and image analysis. Thank you for listening. I'd like to thank my colleagues from the ACDC team at UNSW and Arena and ACUP for funding. And if you want to learn more about what we do, here is the list of our presentations all throughout the conference.